In this video, we are going to learn about how we simplify radical expressions with variables. So radical expressions means roots. So when we have variables inside of roots. So first, some key properties. So if I have a root and there are things getting multiplied or divided within it, and if I call those numbers a and b, and the type of root, this n, it's a positive integer, what we can do is we can distribute the root. So this becomes the nth root of a times the nth root of b. I'm allowed to distribute a root when the things inside are multiplied or if they're divided. So here I'd get the nth root of a over the nth root of b. I'm allowed to do that as long as all the radicals involved here are defined. So if I had something like the square root of a negative number, ooh, that's undefined, and I couldn't apply these properties if I saw something like that show up at all. Remember, we're not allowed to distribute a root if we're adding or subtracting things. So if I had square root of a plus or minus b, it's really tempting to say, well, does this equal the square root of the first thing and then plus or minus the square root of the second thing? But it doesn't. We've seen this before for exponents, that with an exponent or now with a root, you can't distribute it when the things inside are added or subtracted. You can do it when the terms inside are multiplied or divided. All right, so now an important thing. If we have an even root of a variable raised to an even power, like for example, if I got the square root, a square root means it's a second root, that's an even root, and the variable inside has an even power, well, the result has to be non-negative. The result's got to be non-negative. Actually, for two reasons. We've seen already that when you take an even root like a square root, the output has to be non-negative. But there's another reason, which is even if you were to plug a negative number in, well, the even power that you have inside is going to wipe away the negative and make it non-negative. But sometimes when you simplify it, we're going to need to put, it turns out you're going to need to put an absolute value sometimes. We're going to need to put an absolute value on our output if it isn't guaranteed to be non-negative already. So let's explore that, because we've seen this a bit before. Well, if I have the square root of x squared, how could I work this out? Well, there's two ways I can think about it. So one is when I'm square rooting something, I want to know what do I square? What do I square to get the thing inside? And the thing inside is x to the 2. So what would I plug into this parentheses to make it work? Well, one thing I might think of is, x, right? Because if I do x squared, I get x to the 2. And it might seem like, okay, doesn't that mean the answer is just x? We got to be a little careful. Another way we could have arrived at this x is we could have rewritten this as a fractional power. Because I can write this as x to the, and then the exponent goes on the numerator of the power. And then the type of root, because this is a square root, that's a second root, that goes on the denominator. So 2 over 2 just becomes 1. I get x to the 1. Oh, and x to the 1 is just x. But we've seen before that we can only do this fractional power thing when the base is non-negative. So if x was non-negative, I could do this. But if x is negative, actually the fractional power thing no longer applies. So I noticed that even if you plug in a negative, this even power will wipe it away. So whatever this is on the left should be non-negative. So the thing on the left should be non-negative. But if you plug a negative number in for x, the right-hand side is negative. That cannot be equal to the non-negative on the left. So as a result, you need an absolute value on this. You need an absolute value to guarantee a non-negative output. And we care about that because what we started with has a non-negative output. Okay, so now what about part B? What if I got the square root of x to the 4th? Well, it kind of seems like what this should be, like if I did my fractional power thing, is I'd get x to the power goes on the top of my fractional power, and then the root, this is a square root, that's a second root, that goes on the denominator, 2, and then 4 over 2 is just 2, I get x squared. So it seems like it should be x squared. The fractional power, I can do that as long as x is non-negative. If it's negative, though, I can't. So does this one need an absolute value? Well, the thing that I'm starting with, if you plug in a negative, the even power will wipe it away. And if I plug a negative into this one, well, this already has an even power. So it's already non-negative. So no absolute value needed. So this one, no absolute value, since it's already non-negative, due to this even power. Okay, so this one did not need an absolute value. I started with a non-negative. I also ended with a non-negative because both of them have even powers. Okay, let's do one more. Part C, square root of x to the sixth. If I do my fractional powers thing to kind of make my initial guess, I'd get x to the power goes on the numerator. A square root is a second root that goes on the bottom. I'll get x to the third. Okay, but remember that only works as long as the x is non-negative, but it doesn't. X could be negative, but let's just write that down as my initial guess. I'll write x to the third. And if I plug in a negative into this, the even power makes it non-negative. But the result, the answer that I have here, if you plug in a negative, there's an odd power, and that would be negative, not non-negative like what I started with. So this as well, it needs an absolute value. Okay. So when you have even roots, like a square root or a fourth root, and you have variables raised to even powers inside of them, your answer sometimes needs an absolute value. It kind of depends on, well, is that answer guaranteed to be non-negative like this? Because then it does not. And if it could be negative sometimes, like x or x to the third could be negative, then we got to fix it and put absolute values. If I have an odd root, like a cube root or a fifth root, absolute values are not needed. They are not needed because it's actually totally fine for an odd root to output a negative number. So if I do my whole fractional power thing for this one, I would get x to the power is 3. And this is a cube root, so that's a third root. I'd get a 3 on the bottom. So this just becomes x to the 1, which is x. And I would just write x, and that's it. I don't need to worry about absolute values because I have an odd power and an odd root. This could totally be negative, and if x was negative, this is negative, but then they still match. Okay, and then finally, if I do b, well, if I do my fractional power thing, I'd get x to the 6 over 3, which is x squared. That's x squared. And again, because it's an odd root, I don't need to even worry about absolute values. If I did, if I were to think about that, because the starting thing has an even power, it's non-negative. But the ending thing also has an even power, so it's non-negative, so there's nothing to fix. That's just our answer. Alrighty. Okay, so let's flip the page. Let's do some examples. Let's up the difficulty a little bit. So let's simplify the following expressions. So for A, I got this square root of 16 x to the fourth. And when things inside are being multiplied, I'm allowed to distribute the power. So I'll get square root of 16 times the square root of x to the fourth. I know the square root of 16 is 4. And then for my square root of x to the fourth, well, we actually did it on the previous page. But just to kind of recap, for my initial guess, I will do my fractional power thing. X to the power is a 4. And the type of root is a square root, so I do a 2. And 4 over 2 is 2. I get x squared. So I'll get x squared. And because it is an even root and there's an even power, I might need an absolute value because this is guaranteed to be non-negative, what I start with. But because what I end with has an even power, no absolute value is needed. Okay, so that is just it. Okay, awesome. So let's try B. So I got the square root of 72 x to the third y to the 5. So this one's tougher because all of the terms, it turns out inside, don't have like a perfect square root. So we've seen that when something like 72 doesn't have a perfect square root, you try to find a perfect square that evenly divides it. So I know that 72, for example, it's 36 times 2, because the square root of 36 is really nice. And I also want to do the same type of thing for these variable terms. Like I know when I do my whole fraction, if I try my fractional power right now on this, I'd get x to the 3 over 2, but that doesn't simplify to a nice whole number. I'd really like the numerator to be even. So, the fact that I have the square root means I'm going to be dividing by 2. So, what I'm going to do is I'm going to split up this x to the third into an x squared times x, right? Because the square root of x squared will simplify really nicely. That'll become x to the 2 over 2. Ooh, and now the exponent simplifies to just 1. I'm going to do something similar for y to the 5th, because right now that would be y to the 5 over 2, which doesn't simplify super nicely. But this would simplify nicely if the top was a 4. So I'm going to split this apart into y to the 4th times y. And now let's do all the roots that simplify nicely. That's square root of 36 and x squared and y to the 4th. So square root of 36 is just 6. Square root of x squared, well, doing this, my initial guess is just x. And I should think about absolute values because I do have an even root and I do have an even power inside. Well, because I have this even power, if I plug in a negative, it'll get wiped away. It'll become non-negative. And if I just look at this, well, if I plug in a negative into this, there's nothing to wipe away the negative. Ooh, so I will need the absolute value on the x. For the square root of y to the 4, that becomes like y to the 4 over 2, which is y squared. No absolute value needed because this has got an even power, so it's guaranteed to be non-negative already. And then all the other terms here don't have a nice square root, so they just get multiplied together. They stay in the root, 2xy, and we got it. Okay, so let's end with one final example, part C here. So, okay, I want to do something similar with the cube root. So I want to first have you try it. So pause the video for 3 minutes to try this on your own. So pause it in 3, 2, 1, pause it and try it. Okay, so hopefully you had a chance to do that. Let's talk about it now. Well, okay, so again, I want to try to separate out the parts that I know have, in this case, a perfect cube root. And I know 27 does, so I'll get cube root, and 27's got a nice one. A to the 6th, if I cube rooted, I would be writing a to the 6 over 3. Oh, and 6 over 3 is just 2, so that simplifies really nicely. So let's leave a to the 6th as it is. B to the 7th, if I did that, would be b to the 7 over 3. Oh, that does not simplify nicely. So I want to separate this into a piece that would. And it would if there was a b to the 6th. So I'm going to split it up as b to the 6th times a b, times b to the 1. Okay, because now the ones I can do perfectly are the 27, a to the 6th, and b to the 6th. Right, and I'm allowed to do the cube root individually on those because the terms inside are getting multiplied together. So cube root of 27 is just 3. That's just 3. For a to the 6th, I would get this, which becomes a to the 2. Similarly, for b to the 6th, I'd get b to the 6 over 3, which is b to the 2. And then it's just this other b that does not simplify perfectly, so that stays inside my cube root. So I'll get cube root of b. We don't need to worry about absolute values when we have an odd root. It's just when we have even roots, like square roots or fourth roots, where we got to worry about that. Okay, so there we have it. That's our answer.